All right, folks, we're going to quickly look at section 3.5, which is the derivatives of trig functions. So the first thing we're going to do is actually look at graphically at the function sine of x. So what I have here is I just have sine of x graphed in blue. What I'm going to do is I'm just going to estimate a bunch of tangent lines all over one period of this function. So I'm going to go ahead and highlight those in red. Just going to get rid of the original function for a second. So you should see those tangent lines in red now. Now, first thing I want you to notice, when I take the original function away, I can see the general shape of the derivative then. And what I can see about those general shape of the derivatives, all these tangent lines definitely look like they form some sort of sinusoidal or periodic function. Now, on first sight, it would look like it's a sine function, but it's not, right? We don't care about the shape of the slopes. We want the values of the slopes. So the values of the slopes I have outlined here. So what I'm going to do now, I'm going to put the sine function back. We have the tangent lines there. I'm going to take the tangent lines away and just plot the values of their slopes. So these are the slopes of those tangent lines at all those points. So again, let's go through that one more time. Here's the sine function. We can estimate tangent lines using our limit definition, which I've done here. There's just a ton of them at a bunch of different points. I'll turn those on. So we can see the estimation of tangent lines if I turn those off. So for example, the tangent line at like pi over 2 is clearly 0. We can see the value of that line is horizontal. So down here in the table, we should see that that value is 0. So now what we're going to do is we're going to get rid of the slopes of the lines that are on, or in other words, tangent to the function, and we are simply going to look at the values of those slopes. So if I take the slopes away and just plot their values, we can clearly see that this has a totally recognizable shape. It is definitely sinusoidal. More specifically, it starts at 0, 1. It has a period of 2 pi. So in other words, we can visually see then that the derivative of our sine function is itself the cosine function. Now the argument is going to be very similar for cosine. We could see it graphically first. So if I go to this graph and I just quickly change our function from sine to cosine, we can see that we'll start to see again a nice recognizable shape. If we go through again, first we'll start with the function cosine, which is here for us in blue now. And then we can estimate the tangent lines at all those points. And again, we can see that the tangent lines themselves are sinusoidal, but we don't want the lines, we want the slopes of those lines, in other words, the values of those lines. So if I just plot the values of those slopes, we can see this very recognizable shape. It definitely looks like a sine graph. It's at 0, 0, and it ends at 2 pi. The only thing is that this sine function decreases first rather than increases. So we can clearly see from this that the derivative of cosine will end up being the opposite of sine. Now, we can do a quick little proof of cosine once we know the definition of the derivative of sine. So like the idea that I'm starting with here is we could just redefine cosine. We know cosine is just sine that's shifted a little bit to the left. So if I come back to this and kind of turn a bunch of this junk off, what we can see is that we already have cosine plotted. So we'll turn cosine on. I'm just going to go ahead and put on another random function. We'll just do sine of x. We won't use function notation right now. So we'll do the sine of x plus pi over 2, and what we'll see is that those two graphs will be exactly the same. And we should know this already from our study of transformations in prior classes. But it's good just to see right here that they are exactly the same. So you're taking my word and visualizing it. So we'll get divided by 2 in there. And we can see that those graphs are the same now that the solid one is on top of the dotted one. So we can definitely see that those two graphs are the same. So we come back to our proof here. So therefore, if we're looking for the derivative of cosine in terms of x, we could simply just rewrite that cosine as sine of x plus pi over 2. So on this side, to find the derivative, this is just a chain rule. We have a function on the outside and a function on the inside. So we use our chain rule for this. So our chain rule would say the derivative of the outside. So we know the derivative of sine is cosine of the inside. and we'd multiply it by the derivative of the inside function. And the derivative of a line, right, just x plus some sort of constant, that's just going to be 1. So what we see here is we've defined cosine, the derivative of cosine, as the cosine of x plus pi over 2. However, if we go back and look at the cosine of x plus pi over 2, so we come back up here and change this to the cosine of x plus, and we'll do pi over 2. What we'll notice, though, is that's just the flip of the sine function. So I'm going to get rid of our sine function. I can just visually see that. If I go ahead and put in like the opposite of the sine of x, we'll see that those are the same functions. So we can also prove it using the derivative rules that we already know. So again, we would then conclude that this thing right here can be replaced with negative sine of x because they are equivalent. Now we do want to look at the tangent function, but before we do that, I want to make a quick note here that the rules that we're going over, like the ones we just said, the derivative of sine is cosine, the derivative of cosine is negative sine, that will only work when the input is radians, and we have to be very explicit about that. Now, it's not required of you, but if x was in degrees, meaning we were inputting degrees into our sine and cosine function rather than just radians, the formula would be completely different. And the only thing I want you to kind of see from that, and again, won't really be responsible for proving this or anything, or really even knowing it, I'll give it to you. But the idea is, if we wanted to take some input theta in radians and try to represent that in degrees, we know the conversion. We would simply take the number of radians we have and multiply by the conversion factor of pi over 180. Because like we said, like we would convert radians to degrees with that multiplier. So then we can kind of see where the derivative function would come from. So in this one that I've written down here, I'm explicitly saying that x is in degrees. So if x was in degrees, the cosine has like a multiplier and has a little bit different types. We see some general relationships, and I do encourage you to look at, again, we see that pi over 180. But if your input is in degrees, these trig derivatives will change. So we're going to be working in radians. So if we know the derivative of sine and cosine, then it's logical to look at tangent just because we know how to define tangent. We know the tangent of some input can just be redefined as the sine of that input over the cosine of that input. So therefore, if we were going to just try to calculate the derivative of tangent, we would just go ahead and use the quotient rule because we can define tangent of x as the quotient of two smaller functions. So our quotient rule would say to take the low d high minus high d low, right? So low d high minus high d low all over low squared. So I'm just going to go ahead and fill those things in. So the lower function is cosine. I'll just show my work a little bit below here. So the lower function is cosine. The derivative of the upper function, the derivative of sine, is cosine. So we have the cosine of x times the cosine of x. Then we have to subtract the derivative of the high d low. So we'll take the higher function, which was sine of x. We have to multiply that by the derivative of the lower function, which we just said the derivative of cosine was negative sine. We have to divide all of that by cosine squared, the bottom squared of x. Now do a little algebra here. We see that this is just cosine squared of x. And then this, the negative and the negative will turn positive, and that's sine squared of x. And we still have our denominator of cosine squared of x. And then we obviously recognize the trig identity, that the derivative of, cosine squared plus sine squared is just 1. So there's your derivative. The derivative of tangent is 1 over cosine squared. So that does mark the end of the content for today. So we are just going to kind of work on some examples. I'm just going to do 2 of them. If you don't feel like you need to do the examples, you could stop. But these will be the 2 examples for today. So we need to find each derivative. So we need to find the derivative of 2 sine of 3 theta. So first we'll just kind of take out that multiplier, use that function rule, but we'll kind of just say the derivative then. So we'll have 2 And then we'll have to take the derivative of sine. So the derivative of sine of 3 theta. So we already have that 2 as a multiplier, so this will be a chain rule. So we'll start with the derivative of the outside, which we know the derivative of outside is sine, so the derivative of sine is cosine of the inside. Times the derivative of the inside, and the derivative of 3 theta in regards to theta is just 3, so that gives us 6 cosine of 3 theta. The last example just wants us to find the derivative of cosine squared, so here we're just going to apply the product rule, right? Cosine squared is just cosine of x times cosine of x, so we kind of just remember our product rule, left d right, and right d left, or any other way you want to remind yourself of that. So in this case, the left function is cosine of x. The derivative of the function on the right is the derivative of cosine, which is negative sine. And then we'd have to add the right-handed function, which again is cosine of x, times the derivative of the left-handed function, which is again the derivative of cosine, which is negative sine of x. So we are just going to do a little clarification here. So we would have 2 negatives, which would kind of cancel out to be excuse me, not the negatives cancel out. We just have 2 of these terms. Sorry. So we have 2 of negative sine of x times cosine of x. So we'll just pull out that negative. So we have negative 2 sine of x cosine of x. Or of course, if you wanted to switch those around, that's fine too. So those are your examples for the trig identities. I guess I can throw one in. As another example, we will find the derivative of, let's do 2 tangent of 3t. I'm just taking one from the textbook. So 2 tangent of 3t. Just so we can kind of see how this is going to work. So we're obviously going to use the chain rule because we have a function 3t inside of that 2, so that, or inside of tangent. So that 2 will become just a multiplier. So the derivative of the outside function, the derivative of tangent, we know is 1 over cosine squared, but it's of the inside, so of 3t. And then we'd multiply that by the derivative of the inside in respects to t, which is just going to be 3. So we'll be left with 6 over cosine squared of 3t.